Assalamualaikum warahmatullahi wabarakatuh. So we continue with chapter number 13, the final chapter in our syllabus or in our subject, this subject. So we want to see the ion permutation, permeation and membrane potential. Okay, so when ion pass through the membrane, so it will produce a membrane potential due to the concentration. Okay, so we have two potential, nurse potential and donor potential. So let's see first for the nurse potential. So we consider two compartments A and B separated by a membrane with a higher concentration of salt on one side than the other side. If we consider that only one ion is present, then that ion will diffuse across the membrane down its concentration gradient from high concentration to low concentration, but the other ion will remain behind. Okay, so this one will produce a charge imbalance and therefore a membrane potential. So the membrane potential that develops opposes the flow of that ion. Okay, so this membrane will stop the flow of the ion, try to stop the flow of ion, the permeant ion, from moving from, let's say, from A compartment to B compartment. But after some time, the equilibrium will be reached where the difference in electrical potential, delta U, perfectly balance the difference in the chemical potential, delta G. Okay, so this is the chemical potential, delta G. Transfer one more from A to B, so A to B, delta G naught plus RT ln CB over CA. So these are concentration of the ion, the permeate ion in compartment A and compartment B. Compartment A and CB is the in compartment B. Okay, and the free energy chain per mole due to the electrostatic energy chain is delta U equal to Z F VB minus VA. So the voltage difference at B compartment and A compartment, where Z is the number of electron, valence electron, and F is the Faraday constant. Okay. So when the two solutions reach equilibrium, so from compartment A and compartment B, there is a zero net change in the energy for ion movement across the membrane. So we have the nurse potential. Okay. So jumlah yang masuk sama juga dengan jumlah yang keluar. Ataupun jumlah yang pergi ke compartment A sama juga dengan jumlah yang pergi ke compartment B. So we have delta V equal to minus RT over ZF ln CB over CA. Okay, so we have this, if one molecule or one ion can permeate, okay, so we can just measure the concentration of that ion in compartment A and compartment B, and also the charge, the number of electrons for that ion. Okay, so if Z equal to 1, CA greater than CB, then VB greater than VB, so delta V is greater than 0. Okay, so we have this equation. Okay, so A, the difference of a voltage is higher at compartment B rather than compartment A. If Z equal to minus 1, CA equal greater than CB, then VB less than VA, so delta V is less than 0. The membrane potential is less than 0. Okay, so the increment in the membrane potential, so RT over F at room temperature 25.6 millivolt. So increasing the concentration tenfold, RTF equal to 58 millivolt. Okay, so there will be a high high energy voltage difference between these two compartments. So in most vertebrate cell, so the difference is 87 millivolt. Okay, so here we can see that the ion, the molecule or the ion will pass through from outer cell to the inner cell. Okay, the membrane potential represents a steady state rather than equilibrium. So steady state, what we can say is that moving masuk ke dalam dan berapa banyak sama juga yang keluar ke luar. Okay, so initial condition equal to final concentration 0.3 micromolar change for in this membrane. So the smaller cells require greater change in ion concentration. So delta C to the 0.03 millimole. And calcium Cb, the concentration at compartment B is less than 1 micromolar. So next we see the dominant potential. In dominant potential, all of the ion but one can diffuse across the membrane. So many ion can pass through the membrane. So the membrane surface is typically viewed as a large polyion like the nucleic acid within the cell. Okay, so this one we are saying that ion in A can pass through the to compartment B, and ion in B can also pass through to compartment B. Okay, so here we can see that the small ion B minus and A plus can flow across the membrane, but the large N ion and minus W are trapped on the compartment A side. Okay, so we're supposed to have the figure. So the ion B minus are pushed to the right, and the ion A plus are put to the left. Okay, so here we are saying that B minus from A side to B side, and A plus from B side to A side. So the build up of A plus in compartment A and B minus in compartment B makes a delta V equal to VB minus VA negative. So the nernst potential for A and B is equal to this equation, but for the dominant potential, A plus B, the concentration at compartment B, compartment A, compartment A, compartment B. So we have this. Okay, so compartment A, the mass chain is equal to this equation, and for compartment B is equal to this equation CB. So finding the delta V using this equation, okay, the equation of the from this equation, so we can get solving for A. So the membrane potential or the dominant potential is equal to this equation. Okay, so RT F ln W. So we measure the concentration of the polyion, and Cb, the concentration of Cb, to calculate the membrane potential. Okay, so we measure the concentration of this. Okay, so then we can know the membrane potential for this cell. Okay, so what are the difference between nernst and dominant potential? In dominant potential, a certain amount of ion flow occurs in order to reach the equilibrium. In nernst potential, the concentration hardly change at all. Okay, because of too many, only the certain ion can pass through. In dominant potential, sudden change in ion concentration, because B move to A and A move to B compartment. Okay, so the last one for this Part 1. So we have the membrane potential. So we have the resting potential. So a stable membrane potential seen in the absence of stimulation. Okay, so bila dia dah kita ada concentration, dah sampai equilibrium, so we have a certain a voltage for that membrane. Okay, so this voltage is a resting potential. Okay, resting potential are generally negative. That is, the inside of the cell is negative relative to the outside. Okay, so it will stop the flow, or it will try to stop the flow of the ion from the inside to the outside of the cell. Okay, so if a cell membrane allow only one ion to permeate, then the cell can concentrate that ion by active transport and then allow it to diffuse back to the out to create a negative nurse potential. Okay, so here we are talking about the active transport. Okay, so kalau meaning that kalau sel kita kekurangan certain ion, okay, so it can pump that ion or allow that ion from outside to enter our cell through this active transport, macam guna pump. Okay, or a cell could make a large amount of polyion and allow other ion to distribute to form a dominant potential. Okay, so here in order to get this resting potential, okay, so produce polyion, maknanya the cell, some of the cell part diffuse or not diffuse, bukan mereput, terurai, okay, untuk hasilkan large amount of polyanion, so that because of this different in concentration of polyanion, so it will make the ion from outside coming to inside, or ion from inside moving to the outside, so to get the equilibrium back. So neuron use K plus ion as a primary medium of their resting potential, so nurse potential. Skeletal muscle of vertebrate use K plus and Cl minus. So these are the dominant potential. Okay, so here you can see that K plus nurse potential and K plus and Cl minus dominant potential. So these are A from inside to outside, and these are from outside to inside, for example. So you can have this resting potential. Okay, so that's all for this part.